Hi everyone. I see people are slowly joining. Welcome to another Memgraph community call. Today I have with me Dinesh, team lead from Volue. Hi Dinesh. And I have Inge, backend developer from Volue as well. So just to give you a bit of intro, I met both Dinesh and Inge first as a part of the community, Memgraph community. Uh, I heard they were kind of trying to implement Memgraph within their solution, and they also provided. I mean, we helped them, but they also provided a lot of feedback to us as well on the product. And I must say they were also a big part of us improving the product. And I was really happy when I heard they wanted to share their story. They were willing to share their story and their use case and what they are doing with Memgraph. So today they are going to talk about how they transform power grid management with Memgraph. They are going to tell us why they are even using graph databases, why Memgraph, a bit about performance, how it is for them. And yeah, I'm really looking forward to learning more about the use case, how Memgraph performs for you, and that everyone else gets to hear it as well. Before we start, I should say that we will do a short Q&A session after the presentation. And you can ask questions during the presentation in the chat or in the Q&A tab. And we are going to have two short polls in the poll section. So yeah, I see people are slowly starting to join. I will remind everyone about this in the chat during the presentation. And for Inga and the national worries, I will read the questions out loud after the presentation, so you don't have to take care of chat or anything like that. And yeah, that's enough of me, I would say. Good luck to both Dinesh and Inga, and thank you for joining this community call and doing the presentation. I would say the stage is yours.
Thank you. I'll just share my screen.
Yep.
Yeah. Just to start with, we work for Volue. It's a company in Norway working with power grid data. It's me and Inge here. Inge.
Yeah. So in this presentation, we will talk shortly about what Spark is and about the power grid. We will talk about the architecture of the Spark project and a bit about different graph technologies. And we will also talk about data modeling in the graph. We will finish up with our experience and some numbers and stats at the very end. First, Nash will take us through the couple of first points.
Yes. Before I really tell you what we are doing in Spark, maybe through this journey, I want to explain what's how the power grid network look like. It's basically a station here, and there's a high voltage power lines or the medium voltage power lines coming into that station, and then it's transformed into the low voltage network. And what we are focusing is on the low voltage network at the moment, but we need the medium voltage data also for analyzing. What we do over here is we have a substation, like I was explaining, that things come into this when the power comes in, then gets transformed, and it is transformed to a lower voltage. And then we have cabinets where it's actually the power comes in and gets distributed to the end users. Here we are the normal end users who are actually consuming the power. What happened was when this was initially set up, it was set up for home appliances. All this network was built for home appliances, and things have changed. We now are going more. We are using more electricity for powering our cars, and very high requirements for powering our cars and water heaters. So what we want to do over here is to make sure that this network is able to handle all the extra load on the system. Typically, distributed distribution system operators, they would need to increase the capability by changing the infrastructure or adding more to the infrastructure. In most of the cases, it's not feasible. It is very expensive, so they need another solution for that. So what we are doing at Spark is to change the behavior of the usage at the by the users or the by the resources to ensure that we do not have too much load on this network. That way, we want to make sure that we are able to serve the people by doing that. But why would these people change the behavior? So without really a meaning to them, they would just go and charge the car whenever they want to, or start the heating whenever they want to. Uh, what what we do is basically provide the necessary services to DSO, the operators, and the distributed energy resources, wherein we are able to say that, okay, if you don't charge during these periods, which we have estimated that the load will be very higher, then you will be compensated for that. So that's an incentive that is provided to the end users. But then there is another scenario where actually you have solar panels generating energy. And that's the time when we have to tell the users, okay, now use the electricity because there is too much electricity available within this. So we try to focus our work within what we call as neighborhood, which means all those end users who are impacting each other. So we need to make sure that within the neighborhood, the load is assigned over there is good enough for at any point of time. Right? Then to do this, what we wanted was we wanted to build up necessary services and build up our architecture around it. So what we had from the beginning is we have an Azure platform. We want to use Kubernetes. We said we can store the data in PostgreSQL, Azure storage, and send the messages across using Event Grid. Then we wanted to develop the web API using .NET, and we want to perform the network calculations that are required to analyze the network situation at any point of time using Python and PandaPower. So if you see what is happening is DSO provides data which is from AMI and the grid data. What we do is we ingest to our storages and process the data. We analyze this data and do a forecast using ML. Forecast trying to say what is going to happen, how much load will be there on this neighborhood at any point of time in future. So using that forecast, we prepare an advice. We find out how or what are the energy resources that are going to be using this network, and we prepare an advice, send it to the DER. DER is the distributed energy resource. So we send it to the DER, and then DER tells us whether the end user has complied to that, and then we prepare a compensation from sorry, from the DSO, and that compensation is sent to the DER. But for us, we are working with a team. We are working in a team which is more interested in storing and managing the grid data. So this is the part we are very interested in because it's the core of all the analysis that we will be doing. Without this it would be impossible to really estimate the load on a system. This is what we are going to focus on. So what we started with looking at the traditional network information system management software, where we have spatial data and the network topology of the grid is stored in RDBMS. They have connectivity rules. The queries go row by row, and have it supports fixed type of traversals in the network, which is essential for performing the calculations and finding out the neighborhood. These are the things that are in the traditional NIST, provides all the information that we need, but at a cost. It is quite slow because the changes in the whenever we make any changes in the data model, you need to recreate the network, you need to rerun the analysis, which would be very time consuming. And the network topology is also created from the geometric coincidence of the geometry, which is like it is derived. The topology is derived from the physical geography, geographic elements. And whenever we have to change anything, we have to really rebuild the network. Whereas what we thought was, this is not the way to really do the network analysis. They are not designed for the network analysis. So what we thought was, why not try graph? Uh, Graph, what we did was we stored the geometry or the geography part in a special database, and then the network topology we stored in the graph, because we think that network topology is about relationships between the objects, and graph databases handle it very well. So, and when we do the traversal, we do it by query, which means we are not fixed to other special functions provided by the system. We can actually create our own queries to traverse at any time, any point of time. And then we would be doing the query by patterns, not by telling exactly how which which object you have to traverse to the next object and the next object. We can just give a pattern in which it should be traversing. Then you can change the data model at any point of time without having to do any changes to the network topology. It just continues to work. Then Inge, you have been working a lot with graph. You can just take over and explain us the graph databases.
Yeah, so as Dinesh said, we figured out we needed a graph database due to how heavily connected the Power Grid data is. We looked into more like traditional RDF databases such as GraphDB. And one plan was actually to have an RDF database in front and then pick what we needed from the RDF database into another graph, but that seemed like a bit too much. Initially, we landed on Tinkerpop Gremlin with Janus Graph. When I think back, I don't fully understand why we actually picked it. I think we were afraid that Memgraph wasn't mature enough, and we didn't want to rely on a single company. And Memgraph is more like a community project where everybody contributes. But we sort of had to rather quickly stop using Gremlin Janus Graph due to problems by getting this into production, and I will get back to that very soon. So when we couldn't use Gremlin anymore, we decided we should try Memgraph, and quickly found out we should have started with it. Then we would have saved some time. Working with Memgraph was just much simpler and less painful than working with Gremlin. For example, we had a query for a specific topology trace that we used around 2 months to get the logic and query in place in Gremlin. And when we switched to Memgraph, we wrote the same query in less than an hour. It's a bit harsh on Gremlin because we still was working out logic, but the main point still stands. Writing the query in Memgraph is way easier. In Gremlin as well, when we're making traversals, we had to make sure we never traverse to the previous node, but sometimes you needed to go to the previous node. And that is just a bit of a hassle to keep track on, and it's tedious work. Whereas in Memgraph, since it's pattern matching, it's much easier to get an overview of the whole topology, essentially. And something also that made Memgraph easy to use is the lab. And you do have similar tools in other graph databases, but wouldn't say they are on par with Memgraph Lab. It's easily the best. Getting back to production a bit, like getting Gremlin set up in production was a little nightmare with all of the different pieces that you needed to talk to each other. Now I don't fully remember everything, but you had Gremlin, you had the graph database, which was Janus Graph, and then you had Elasticsearch. But with Memgraph, you have one container, one image. That's it. That's all you need. It was by far the easiest to set up. We also had Neo4j in our mind, but it's no free tier and it's a high cost. It's a sort of a lock-in type situation. So if you go for Neo4j, you're sort of stuck with Neo4j. And there we have like open source versions, something like Memgraph, which is much less scary to start with. We can't avoid talking about performance as well. We need a fast solution for our project. Sorry. And you could get a fast solution by using Gremlin, but again, the time getting it ready and setting up in production and stuff is just not worth it. You have Neo4j, but again, that's a disk database compared to Memgraph that's an in-memory database. You don't need to spend a lot of time figuring out that one is going to be a lot quicker, and that is, of course, Memgraph. You can go next slide, Dinesh. Yeah. Something that has been crucial with this project is the modeling of power grid data in Memgraph. This is going to be a bit technical because we need to talk about the model and the data itself, which is SIM data, which is one of the most common format to exchange power grid data. As we have mentioned several times, it's very highly connected with a bunch of different entities, and several of these entities are abstract, like they don't actually exist in the real world, only in the data. We have a small customer, as you can see, 912,000 nodes and 2.6 million edges. So it's many one-to-one relationships, but there is also many nodes that are one-to-many relationships. A pretty classic example is you have like a power line, so we can see the AC line segment in the left corner, and that connects to a cable box that has multiple switches. Now, switches is just like a light switch. It decides whether power goes through it or not. Now, in real life, the cable would just be essentially just screwed, so it always connects to the switch. So metal connects to metal, and then you can conduct power through them. In SIM data, you have 5 different entities for it. You have the cable, you have something called a terminal, you have a connectivity node, and another terminal, and then finally the switch. So in the data would look like you see in the bottom left corner. You can quickly see that the terminals are the edges and not the AC line segments. Despite AC line segments being the actual long physical cable in the grid, it wouldn't make sense to have it as a edge, considering it doesn't actually explain what is connected to what. That is what terminals does. And for example, and the relationship is the most important thing here. If I start at an endpoint, let's say a house, and want to traverse to find the other houses that it's connected to, because a major power draw in one house will have an effect on the other house, as Dinesh mentioned at the start. If you go next picture, as I said, you need 5 entities to explain how it is connected, but we have more information about the nodes, and this is also placed in separate nodes. We're following the SIM structure pretty much here. So you have information about the base voltage, you have information about what type of resource type it is. So an AC line segment could be a high hanging cable, a low hanging cable. It could be a cable that goes underground. And since this is information that is going to be used by many nodes, it's the most logical thing would be to have it as separate nodes and not like not properties on the nodes themselves. As you can see in the picture, all of the nodes have a label that is a single letter N. We picked this since Memgraph documentation uses this at times, so it was the most easiest thing. When we start a query, we almost never know what type of node we start in. So we index the N label and an ID, so we can always start the query as quick as possible and get the best performance. One final thing here is having a direction in the graph. Now, Power Grid sort of doesn't have a direction because power flows both ways. So mostly the relationships that we make by ourselves, which is like is type, reference to, placed in, and owned by, for example, they have a specific direction that we chooses, whereas the electrical part, which is the terminal, should in theory not have any direction, but we chose to have connectivity nodes always point to an equipment, and an equipment will be baseline segment, switches, power transformers. And by having this direction, we can specify when to stop traversing or continue to traverse. So if a connectivity node is connected to a power transformer, we can almost certainly say that we don't want to traverse over that node anymore. And then we can isolate smaller parts of the graph and then do topology searches on that specific subgraph, essentially. Moving on to deployment. Dinesh.
Yeah, I had been working with other NIST systems many times, and then what my experience with the NIST system is that earlier I worked with one system which actually took many days to create, set up, and then test the rules, create the rules, test the rules, making sure that everything is perfect, and then you start importing the data into that one. And then importing the data takes about 8 hours to just import it to an intermediate format, and then convert that intermediate format into the real model in the database. And then to again from that model, you need to generate the topology, which takes another couple of hours. So this is like when we have interactions between two systems, when you're getting the data from one system to another system, it takes a hell lot of time for actually migrating the data into the newer systems. And similarly, we tried to do a better work on the another system, which took us about 3 days to deploy the system itself. And then after improvements and lots of automation, it was like 4 hours to import the data and 6 hours to build the topology. This way, we just ended up with the NIST systems, which were really time consuming and taking a lot of energy from us just to set up the systems, and everything, even after being automated, not good enough to get the data in the real time. This is where we want to use graph technology, and this is where our Memgraph has helped us a lot by just creating services and pushing the data through the services in almost real time. Inge?
A bit about performance, as I said. I feel like there is not too much to necessarily talk about here. Number speaks for themselves. But what I can say is that the top one is downstream trace. So essentially, you start at a specific location and then you trace down into all endpoints, in the sense where you can trace down in a power grid at all. It is worth noting that the data set we have tested here is not exactly the same, which we admit is a bit misleading. The reason for this is that the customers we have in Memgraph simply doesn't have the old NIST systems anymore, and we didn't want to spend time to upload everything to get the same data in two different databases. So the data on the right side is admittedly from a different data set, but the point still stands. Few milliseconds compared to around 2 seconds approximately. In the bottom part, you have a connected trace, which is when you start at any node and then you just find everything that is connected to that node. And then you, again, you can see the times. It's also something that I'm gonna mention is that the times from Memgraph, which is on the left side, it is simply just screenshots from a Memgraph Lab. But if you were to do, if you were to enter the Memgraph container and use MG console, the times would be a bit faster. So like connected trace, it's especially noticeable when you get higher and higher amount of nodes or features. The MG console will be always a bit faster as well compared to normal Memgraph Lab. Yeah.
Yes. Yeah, but I just want to add some more things over here. Now, although we are talking about the downstream trace and the connected trace, to be able to come to that point where we start the trace, it takes a lot of time in the traditional NIST systems. So, if in a NIST system, if you edit, then you have to rebuild the network topology for that particular area and ensure that all the connectivity between the geometric coincidence is perfect to be able to come to that place. But in our database where we have geometry, even if it is not coincident, we don't care because we just tell that topology is connected, and then we can straight away perform the necessary traces. Yes, we have some experience with the Memgraph support. Inge?
Yeah. So we started out with just using the Discord, which helped us a lot. But the more we used Memgraph, the more help we got. We ended up having a private channel in Slack, which helps us a lot. Having more or less direct the option to like directly contact the developers is super, and that means that we can work on queries and optimize our queries way faster than we would before. We also hang on. Yeah, use the Helm charts that Memgraph gave us for deploying it in Kubernetes. Generally, just the experience with working with Memgraph when it comes to support is very good. I don't know if you wanna add anything else, Dinesh?
Yeah, it's just that whenever we got stuck, whenever we needed any help, we got it immediately, and the issues were addressed, yeah, almost immediately. I mean, we just had to write it in the Slack channel that we have, and I think we got the reply in few minutes. It's like not it never crossed a day. We got at least the reply that okay, we will look into this, or we always had a chat with them explaining what the problem was. We started immediately debugging the issues, and we have regular meetings with Memgraph, which we use to follow through with what is happening, and we are always updated about what is going to be coming in future. from the Memgraph's roadmap. And I think one of the features that we requested Memgraph was about spatial support, spatial data support. And yes, we already started getting some support, and in future it's probably going to get much more support, which will help us actually remove our current spatial database where we are storing the data. We might just completely move to Memgraph. Yes, I think that was what we had.
Yep.
Thank you, both Inge and Dinesh. I think the presentation was really nice. You really gave us just a sec, let me. Okay, I'm here. You really gave us a great overview of the stuff that you're working on. I have a couple of questions. I was kind of intrigued with the part where Inge, you said that you were considering RDF to begin with, and that combination of stuff. So. Can you maybe tell me like what was the decision factor in the end? Like, what do you think about? Do you have an opinion on RDF versus LPG? Did you consider that, or
No,
I mean, label property graph versus RDF rich data?
so the as I said, the original plan was actually to the data files that we get, the SIM files, they are containing a bunch of information that we don't necessarily need. So this first plan was to take the SIM files raw and just insert them into an RDF database. We found people had done that before, but essentially we didn't need everything that SIM files contains. So that's why we wanted to use the, as I said, just as a front storage. This is where we upload the SIM files, and then we pick what we need, and then we build a proper graph out of it. We never sort of thought to use RDF for the main database. So yeah.
Yeah, okay, makes sense. We have one question, so let me put it here on the screen. So how did you use CIM when creating the graph database in Memgraph?
Yeah, maybe I can explain this. What we did was we read the CIM files, which is kind of a RDF store, RDF data store. And what we do is we parse it into our own models, and we only extract the things that we need for our the topology, and the ones we like the geometric information also. So the geographic information we just send it to the Postgres database, and we the extracted topology information is what we send to Memgraph. That's how we are transferring the data from that SIM format to our that's a process we call as ingestion, and using this ingestion process we get to the graph database.
Okay, thank you, Dinesh, for answering this. So you also were talking a lot about deployment. So I was wondering, did you ever research anything other than Azure that you mentioned? You were talking about how you deploy there. Was there any other option?
For us, yep, Inge, you.
Yeah, no. Since we are part of a larger company, they set some rules and regulations we have to follow. So we are locked into Azure. For example, Google Cloud and AVS is not an option. We did try to get some trials when it came to Neptune DB, because we read good stuff about that as well. But since we weren't allowed to use AVS, we ended up discarding that. I also just want to mention, like, when we asked around, we got a recommendation to use Azure Cosmos DB, but that's not a proper graph database, even though they claim they are. It's just a NoSQL database pretending to have graph capabilities. We did try some things with Cosmos DB as well. That was just performance-wise horrible. Didn't do us any good.
Yeah. I just want to add one more thing. And we are basically using Kubernetes for our deployment, which means it should be possible for us to be able to deploy in any other system. It's not necessary that we have to be locked to Azure. And for that matter, what we also do is initially when we started, we deployed local Kubernetes on our PCs and tested all these things before we really went into the Azure part of it.
Yeah, thank you. We have another question from Max. I'm bringing it onto the screen. Just a sec. So can you go into a bit more of your reason for pulling out the voltage as a node type rather than an attribute? And does it cause hotspotting or super nodes?
Yeah, so our reasoning for one of the main reasons for pulling voltage as a node is because it's its own entity in SIM, and we had a goal to be as SIM-like as we could be. The other reason is since so many nodes uses voltage level, it feels like it's a bit redundant to have the property on all of the nodes. So that's why it's easier to just have a relationship. And when it comes to supernodes, not really. As you saw, like in a normal customer, which is 1 million nodes and 2.67 million edges connected to 2.6 million edges, it's not that much. If you think about social media, for example, LinkedIn, that is also built on that also uses graph technology. I think Google has like 36 million followers or something. So like the DSO wise and base voltage wise, I don't think we're ever gonna hit an issue with supernodes. It's also worth noting very quickly that each DSO will have their own nodes for everything. So a base voltage node for one DSO won't be the same for another DSO. And it's also important to separate the data completely. So one DSO can't accidentally, by doing accidentally doing traversals into another DSO's data. That's why everything is separate, even the base voltage nodes for the different DSOs.
There's also an impact on this when you're ingesting the data. Since SIM has base voltage as separate entity, every time if you want any other entity to be getting the actual voltage value, then you have to traverse within SIM while ingestion, which is not a. I don't think it's not a good. I think it's not a good idea to do that way, because then you are actually adding on to the time of ingestion. But then at the same time, when we did this work with Memgraph, we try to understand how would it perform, and what we noted was that there was no performance issue for us because of this, and that's why we stuck to this idea of having a separate node.
Yeah, I think that makes sense. If you stumble upon some bottlenecks, you would probably have to tweak the model. And as we always say to the users, like you always have to check first your queries, what you plan to run, see how they perform, and then kind of tweak the model based on that. It's very hard to get it right at first. Okay, and we talked a lot about performance, speed, and those stuff. Can you maybe give us some more info on the kind of queries you're actually running to get the data to your customers? Like, what kind of queries are those?
For the graph, it's a short and easy answer. It's mostly topology queries. It's start somewhere in the graph and either find everything that is connected to that point, whether it is whether it is stuff that is connected with or without conducting power. So you could find what we call a neighborhood is everything that is connected that conducts power. But you could essentially have like multiple neighborhoods connected together, but it's like just one connection that doesn't conduct power. It's a switch that is turned off, on, off, and then you can have like queries that finds every single neighborhood connected together as well, even though they don't conduct power. Also, queries we typically run is if you have a substation, whether it is like a huge substation or just a cable box, find every switch that is inside that that cable box or substation.
And we extensively use the BFS and DFS algorithms provided by Memgraph, which actually changes the query into one single line. And if I had to do this query in a normal place, then it would be like 20 lines of code, and which is actually converted into just one line.
Yeah, I get it. And with the filtering that you can do inside and everything, it helps a lot. Okay, that's really nice. And you mentioned some spatial queries. Of course, you have also another system for spatial data and so on. But what kind of spatial data support do you offer? Like, what kind of stuff can you do with spatial data?
Yeah, well, what we are doing with the spatial data is trying to calculate the polygon, which is actually part of the neighborhood that we call as neighborhood. We try to calculate that polygon. We use a function called convex hull to generate those polygons. And we had a discussion with Memgraph on that, and then that's one of the things that we need so that we can proceed with moving to the spatial functionality that is provided by Memgraph. That's one of the things, and then we also have another one where we are trying to see what is intersecting what. And the thirdly, what we are also doing is we are using this for generating the vector tiles for displaying in the map. So what we do is we take the content, we just generate the vector tiles, and that vector tiles is what is displayed in the map, in a map using web browser, and that's where you can do the queries directly to our system. These are the few things that we would just want from Memgraph so that we can really migrate to Memgraph.
Yeah, then fingers crossed that this features get out soon. No pressure, core team. Yeah, also when talking about data modeling and properties versus nodes and so on, do you have any properties on edges? I mean, do you have a weighted graph or not? Are you using that?
One more time.
Do you have a weighted graph? So do you have weights assigned to edges?
So we do have properties on the edges that comes from the sim data. The edges we create ourselves, just essentially keep controlled relationships. We don't have any properties. As I said, we do have properties on terminals, which is what comes from sim data. When it comes to weighted graphs, it sort of doesn't, in my opinion, it sort of doesn't work for the power grid. There just isn't enough different paths for it to actually be relevant. So you could have two different paths, but they will most likely, in 99 point something% of the cases, it will be the identical path. You could come with the argument that cables have resistance, and some cables have higher or lower resistance than other, but it won't be a big enough impact when in real life. Essentially, it might be an impact for the graph when we're just looking at it on the screen, but in real life, in the power grid, the resistance won't have too much of a difference, and it's just and anyways, the resistance lies on the nodes and not the edges themselves. So it would be a mess to rewrite rewrite the data from from nodes to edges. The impact of weighing graph just isn't worth compared to the work we need to do, essentially.
An impact of the edges is really very useful when you're doing the calculations in the network. And for that, we are actually using another library, which is a Python-based library. So we have the ML team, which is actually using this library to calculate the network attributes. So that's how we are doing the forecast of the system, and we are saying that okay, these are the parameters which are changing in time, and we expect this to be something like this in future. So how should it actually calculate? Based on those new parameters we calculate, and that's how we predict the network load, the total load on the network in future.
Yeah, makes sense. And we have another question related to that. So do you plan to look at predictive maintenance? Do the cables or kit wear out, and could graph help there?
Yeah, we are not into the predictive maintenance, but what we are into is changing the behavior of the end customers. The maintenance is not functionality that we have as of now. But yes, because we are already doing the prediction, this can also be used for maintenance.
Yeah, definitely. So maybe one day, you never know.
Yeah.
Okay, I guess we had a lot of questions. Maybe to wrap up, one last one from me would be, how would you say utilizing a graph database, I mean, in this case, Memgraph, but in general, and having this speed, performance, and having fast deployment and so on, how would you say that kind of affects your end customers? What is the impact of a graph within your system for them?
I would just say that some things they would do in which would normally take them to do in days, now they get it in seconds. So it's a major impact for us. I mean, the end customer is not even noticing it because everything is happening behind the scenes. They have no idea. I mean, the web maps when we used to work, we had some analytical map which click on an object and it would trace. It takes about few seconds, like about 5 to 10 seconds to get the drawing back onto the map. Now we are able to do it in milliseconds. So suddenly when you click on that and suddenly it appears, it's a major change for the way we work with the systems. And of course, one of our developer who is asking for more all the time. There is a developer who's asking for more performance, more performance. So
Yeah.
we are trying to change the whole settings to improve the performance as best as, and then that's where we take a lot of help from Memgraph to change our queries, how we make the queries, and we actually share the query and say, okay, how do we design this query for a better performance? What we should not be doing, what should we be doing, which would make us. And this is like we get help very quickly. That's why we are able to continue with that kind of an environment. Otherwise, it would have been a very difficult task for us also to really give that kind of a performance that we are able to provide as of now.
Yeah, I get it, definitely. And I mean, it's a good thing that we are on the same path to getting to the best performance, as we are striving for that as well. So luckily that aligns. And yeah, we don't have any more questions. I think this also was really nice. Thank you both for answering all of these questions and for participating, for presenting, and giving us a bit of glimpse into your world of power grid management. And yeah, I think that's it. Thanks to everyone else who joined as well, and to ones that will be watching afterwards. And that's it. Thank you again, Dinesh.
Yep. Thank you.
Yeah.
Bye, everyone.
Bye-bye.
Bye.